Okay, we'll talk a bit more about the people that worked with you. And especially when you came to Tucson, you had lots of students coming to you and working with you. If I were to think what is the greatest legacy of Shlomo, it's not only your work, but also the people you trained and you converted into researchers and academics and whatever. So let us remember some of them. In unsaturated flow, when you came to Tucson, you kept working on unsaturated flow.
Well, when I came to Tucson, I found a few students literally coming at the same time. My very first student, certainly one working on unsaturated flow, was Dan Stevens, who did a very interesting work related to the question of how to determine the hydraulic conductivity of an unsaturated porous medium, the Vadel zone essentially, above the water table, by allowing water to infiltrate into the Vadel zone through a borehole. Here in Tucson, his PhD dissertation consisted of running a numerical model, investigating this numerical model. Later he became a professor at Socorro, New Mexico, where he actually conducted field experiments with this effect. And today he runs one of the most successful consulting firms in groundwater based in Albuquerque. Other students that came when I came here were included Graham Fogg, who did his master's thesis with me, partly on inverse methods. Mark Boggs, who did his master's thesis with me and later went to work for Tennessee Valley Authority. Did some interesting work on the interpretation of the Made experiment together with Gelhard and others. Then Britt Jacobson did a PhD on inverse methods as well. Nothing to do with the unsaturated zone, but some very interesting idea of what to do when you have too many parameters in a problem, how to reduce the dimensionality of the problem using some methods developed in geophysics. She later worked at Pacific Northwest Laboratory at the University of Nevada. I think she's one of the regulatory agencies now.
Elon was here at the time.
And
also.
Elon, well, now we kind of move to a different topic, and that is the topic of transport analysis. Elon did some, well, let's go back maybe to some of the work we discussed before, and then I'll come back to Elon because his approach was a little bit different. We talked about the modified method of characteristics and techniques based on that. I had a postdoc by the name of Shaul Sorek, who is well known in this area, and he has done much of this work. I had a PhD student who literally extended the modified method of characteristics to multiple dimensions, Ralph Cady. He has been working at the Nuclear Regulatory Commission for many, many years. As far as transport is concerned, I think in that these were the two numerical methods, but then Elon Adar, who came to us from Israel, just like Shaul Sorek, by the way, Elon did something completely different. He extended the concept of a mixing cell model that was originally developed here by one of our faculty members, Gene Simpson. And yeah, Mike Campana was his student, correct, was Gene Simpson's student. They worked on this concept. But in surface water hydrology, Dave Woolheiser came up with a mixing cell model for rivers. And it was really that version that Elon single-handedly and somewhat contrary to my suggestion developed into what turned out to be an extremely successful practical tool to characterize groundwater basins in areas where there is chemical information or isotope information but virtually no hydraulic data whatsoever. And he was able to apply it here to Aravaipa Valley, and later when he returned to Israel, he was able to apply it to the Jordan River. In fact, across the Jordan River, both Jordan and Israel, very, very successful. He now heads a very, very nice and successful water resources research center called the Zuckerberg Institute, which he was instrumental in setting up and is now heading that. The reason I recommended against the mixing cell model is because it's very different from the transport equation that we normally do, and frankly, This was another case where I was a little short-sighted. He was adamant in pursuing it, and he did come up with really interesting results, something that to this day he has been using with great success. I think as far as transport is concerned.
Yeah. At that time is when the Oracle site started working as well.
Yes, yes. So I had a number of students working in various capacities on fractured rock investigations at the Oracle site. I mentioned Paul Shea, but there were many others doing work there. Many of the data, packet test results and so on, collected by Paul Shea were analyzed by Joe Deppner, who wrote a very nice master's thesis. I was extremely lucky to have not only talented PhD students, but very talented master's students with whom we published some rather influential papers, and Joe Deppner was one of them. We, of course, took out core samples and did geophysical work at Oracle, and that was analyzed by Jay Jones, who I don't remember who his advisor was because he was a geophysicist, but he certainly was working with us on the Oracle project. And then some of the concepts with regard to the modeling of fractured flow and transport through fractured rocks that started evolving in the context of the Oracle project, this granitic fractured rock project, were translated into other sites, other areas. So for example, we revisited a very famous study by the French hydrogeologists Guillain de Marcilly, Cacas, and others on a site, and a fractured granitic crystalline rock site called Fanay-Auger, a uranium mine, where we applied some of our continuum stochastic approaches. And that was done by another very talented master's student by the name of Kenichi Ando. He who has, I think 2 or 3 years ago, completed a PhD at the University of Kyoto on a somewhat different topic, but he's heavily involved in nuclear waste disposal issues. In Japan, I had another very talented Japanese master student by the name of Yoshihide, or Hide Shinchi, who is also currently working on nuclear waste disposal issues in northeastern Japan. As far as
quite a bit of field development in these areas.
We did a lot of field work. I sent my students out to the field, stayed in the office, and let them do the field work. But there was a lot of very interesting field work that we have been doing both in crystalline rocks and, of course, later in unsaturated fractured rocks at the so-called Apache Leap research site near Superior. I think I mentioned the work of Walter Illman and Monty Veselinov on cross-hole tests, but that was preceded by many, many meticulous single-hole packer tests conducted there by Amado Guzman, who was another one of my PhD students. I'm trying to remember if there was anything else we did there. I think that was just about it as far as fractured rocks are concerned.
So let's switch to your recent lover, stochastics.
Stochastic method. I had a good group of students doing various types of stochastic analyses with whom we published a large series of papers. Some of the early work on effective permeability, for example, was done by Evangelos Paleologos, who later taught at the University of South Carolina and is now back in Greece, teaching, I believe, in Crete. That work led to further extensions, coming up with three-dimensional stochastic-based expressions for effective hydraulic conductivity of a block in an anisotropic, strongly heterogeneous domain, which was done by Daniel Tartakovsky, who is interviewing me among other things here today, who did also other things. He, in fact, was the first one to continue the work of Shlomo Orr, who worked on steady-state moment equations. Daniel developed transient moment equations and did a lot of work associated with that. He's now a professor at the University of California in San Diego. there were related works which were not necessarily, would not fall into the category of moment equations, but they're definitely stochastic flow and transport. So for example, Yu Kwan-sung, who is a professor at the University of Iowa and is currently spending half his time at the Nanjing University in China, developed some very nice nonlinear solutions for, or expressions for dispersion in heterogeneous media, both pre-asymptotic and asymptotic, which we were able to compare to some of the field experiments done by the Waterloo group at the Borden site in Ontario, Canada. A student who is presently a professor in Taiwan at the Taiwanese University, Kuo-Chin Su, did beautiful work on higher order approximations of first moment, second moment of velocity in a random permeability field. Don Chia Tsang, some people know him as Don Tang, who has done a huge amount of work, very original, but falling somewhat outside of what we have discussed here, on stochastic transport simulations, both Monte Carlo and otherwise, in random velocity fields. We have a series of 5 papers on this in the Journal of Water Resources Research, and also he extended moment equations to include diffusion or local dispersion in them, something that many times is disregarded. He is now he holds a chair at the University of Southern California. He is also a founding associate dean and professor of a brand new school of engineering at the top university in China, Peking University. In terms of stochastic,
wasn't Sukuo working on similar things?
Kuo-Chin, you mean, or
Kuo-Chin Su, probably you mean.
Yeah, Kuo-Chin Su. I mentioned Kuo-Chin Su. Kuo-Chin Su is the fellow who did higher order approximations and is in Taiwan now.
What about Yoon Jang?
Before we go into Yoon Jang, let me just mention Abel Hernandez, who did the first inverse solution of moment equations, stochastic moment equations. Now, if we move from that topic to scaling issues, then we come to Yoon Jang-Hyun from Korea, who is now at the University of Seoul and was here, by the way, so was Abel here yesterday, and Kuo-Chin were here also yesterday, and I was very happy to have them at my 70th birthday celebration here. And so many of the people I mentioned, by the way, were here, some were not. But Yoon Jang essentially took this abstract scaling work that we discussed earlier at some length and showed how it in fact could be applied to some of our measurements of air permeability at the Apache Leap research site. We had permeabilities on small scale measured, we had permeabilities on large scale measured, and she was able to connect them through these abstract scaling theories that we discussed before.
Then there was also Jimin Lu.
Yes, indeed, we did. This is really a combination now of unsaturated flow and moment equations. We tried to apply moment equations to nonlinear problems. The only way to do that is by linearizing the flow equations. So we really took 2 approaches to this. One was the more traditional so-called Kirchhoff transformation that Tsiming Lu, a PhD student who is now at Los Alamos, together with Daniel Tartakovsky and me, did on unsaturated flow. And then I had a student from China, Donghai Wang, who, and also a student who is now in Israel, Orna Amir, who tried to solve nonlinear stochastic flow problems by assuming that the solution is Gaussian. And if you make that assumption, which may or may not apply under some circumstances, they were also investigating the degree to which they apply, they were able to solve to essentially come up with moment equations which don't involve integrals. really that was the main idea. We later learned that something similar was done some years earlier, not exactly the same way as we did, by Professor Morales too of Colorado State University. The way we learned it was by sheer coincidence. We were giving a presentation at the American Geophysical Union meeting, I believe it was, in San Francisco, and he was in the audience and he came and told us about his work. So that was very interesting to discover, you know, something similar to that was tried by others. We did not pursue that too much because we came to the conclusion that the Gaussian assumption is a little bit too restrictive. But it was certainly one of those attempts to solve stochastic equations by whatever means you have in your hands.
Erik was also, Erik Morales also.
Erik Morales, I believe, he has completed his PhD about 2 years ago and was a postdoc with me over the last 2 years. Erik Morales has brought the level of solving stochastic transport equations to where we are now. I would say that both his theoretical framework and the numerical approach that he used is where we are now, and we frankly are somewhat stuck. We are not sure just exactly how to extend this because his approach works beautifully for mildly heterogeneous media or for strongly conditioned things. But when you come to problems in which the permeability is allowed to fluctuate to a large extent, we really don't know today how to resolve this problem. There are some ideas that Don Chiao and others are pursuing, such as stochastic collocation methods and so on. We have not done that, but he and others are doing that, and I'm hoping that those techniques perhaps will help in coming to a workable solution to these stochastic flow problems. There's another student that I should mention, and his name is Wenbin Wang. Wenbin has done very interesting work on trying to interpret data that Professor Peter Varenga and some of his students and colleagues have done at a field site not too far, called Maricopa. The University of Arizona has a farm, an experimental farm at Maricopa, not too far from Phoenix, where they have done several large-scale, deep field infiltration and tracer experiments in the unsaturated zone, way above the water table. Scale of 50 by 50 meters horizontally and about 13 to 20 meters depths. And there's a lot of very interesting data there, which Wenbin has partially taken. And one of the questions was, to what extent can one use so-called pedotransfer functions, which were developed by Riem van Genugten and Simonek and others at the University of California in Riverside, essentially providing you with a way, and Marcel Schaap, who's now here also, a way of translating information about soil texture, how much sand, how much silt, how much clay, how much gravel, and soil density, into hydraulic parameters. He tried different techniques of using these pedotransfer functions to predict, based on soil texture data, what is the distribution of hydraulic conductivities at this site. And then he used that to predict measured distribution of water contents as a result of infiltration applied at the surface. He found that the predictions were not really completely satisfactory based on these pedotransfer functions. Then he applied inverse methods, formal inversion, and he found that that really improves things quite a bit. So he came to the conclusion that if you can, use inverse methods, don't rely on pedotransfer functions alone. But of course, many times we don't have the luxury, so pedotransfer functions are certainly better than not using anything else. I now have a master's student, together with Professor Marcel Schaap, who is continuing this work. We have done some additional drilling and have taken out additional soil samples, sent them to the Riverside laboratory, and they just now have returned some measured values of hydraulic conductivity, unsaturated properties, and so on. And this master's student by the name of Fung, his last name is Fung, is investigating them right now.
Related to this is work you've done on instability.
And I had students one student, one postdoc doing work with me on instability, indeed. Sasha Tartakovsky, the brother of Daniel.
No, Daniel is the brother of Sasha. And husband of poor guy.
Sasha, who is now at Pacific Northwest Laboratories, has done a very, very nice theoretical work on wetting front instability, which followed an earlier review of the literature by a postdoc called Go-Liang Chen. And we published a very colorful report for the Nuclear Regulatory Commission, where we reviewed the literature essentially, and there's a lot to review there, on what is known about instability, both in fractured and other media, of wetting fronts specifically. The focus was on wetting fronts. And then with Sasha, we published a paper in a fluid mechanics journal where we have essentially done kind of a stochastic analysis of wetting front instability under uncertainty in randomly heterogeneous media. There's another interesting sequel to that, which absolutely has nothing to do with that particular work. After Sasha has moved to work in national laboratories, first in Idaho National Laboratory and now in the Pacific Northwest Laboratory in the state of Washington, he started working with Dr. and Professor Paul Meekin, who was a professor at the University of Oslo, but also works at the National Laboratory in Idaho, on a new method called smooth particle hydrodynamics to model in detail, and you know about this, to model in detail flow on the pore scale. And so we just published a paper also in Geophysical Research Letters on the process of mixing and channeling on the pore scale when you introduce a tracer into a steady state flow regime, what happens to it and how the speed with which the water flows would impact the interplay between channeling and mixing, and how this impacts the apparent advective porosity, the porosity that one uses to calculate the velocity at which a solute propagates through a porous medium.
Which I must say that even though we discuss about the actual interpretation of the data, it contains some of the most beautiful solid transport simulations I've ever seen.
Yeah, but they're very interesting. They really give you a lot of insight into this.
Absolutely.
Yes, yes. I'm very lucky in being able to continue collaborating with my students years after they leave here, you know.
Thank you very much, Shlomo.
Thank you for the interview.